Computer Intelligence Applied Research Cluster is one of the research domain of the School of Engineering. We specialize in various research projects in advanced electrical machines in application for energy efficiency. The cluster is headed by Dr. Aravind, with some of our research work is on the development of small-scale vertical axis wind turbine, energy efficiency building solutions, and development of double magnetic circuit machines. Currently, we are developing fractional horsepower machines including BLDC machine, IPM machine, synchronous reluctance machine, and switch reluctance machine. Few of the new machines developed recently are patented for the novelty under the Malaysian Patent Act and also participated in the national and the international summit and conference. The projects are themed towards the 21st Grand Challenges in Engineering through the engineered tools for scientific discovery. We at the center are embedding and folding to put Taylor School of Engineering a spot to provide solutions for the future through our inventions. The simplest way in solving the environmental problems created by vehicles with internal combustion engine is the development of electric vehicles. The conventional vehicle is added with electric propulsion system to the internal combustion engine, forms the hybrid electric vehicle. It is now a popular development for it being energy efficient and environmental friendly. However, hybrid electric vehicle consumes lesser fuel when the internal combustion engine operates at narrow speed region. For this reason, hybrid electric vehicle requires a platinary gear system for continuous variable transmission function to power split. Yet, given the fuel gear ratio of platinary gear system with low power rating and efficiency is not suitable for an internal combustion engine. Apart from that, its electric propulsion system uses permanent magnet machine, operates based on the magnetic flux established by means of electromagnets from armature conductor and permanent magnet. With the relatively high torque requirement for hybrid electric vehicle, permanent magnet machines have been continued to research for torque improvement. The research was then started by studying the magnetic flux linkage of a conventional IPM machine using finite element analysis. However, there are various designs of conventional stator and rotor poles. Thus, each stator to rotor pole combination was evaluated to select the design with best torque performance. Through this evaluation, it can be observed from the conventional single rotor machine that the magnetic flux around the stator yoke is not utilized. It is crucial to utilize the magnetic flux as air gap flux linkage since it is the main contributing factor to torque production of the machine. This can be proven through the general equation of torque. To maximize the use of magnetic flux, an outer rotor is proposed for the conventional IPM machine. As a result, the outer rotor of the proposed double rotor IPM structure, which utilizes the magnetic flux, increase its torque producing point. Meanwhile, the outer rotor structure which nullifies the effect of torque pulsation occurrence from the inner rotor allows the reduce in air gap length. With these two advantages on the proposed machine, the increase in torque performance can be proven through magnetic circuit analysis. As shown in the figure is the magnetic flux path of the conventional IPM machine. The magnetic equivalent circuit and equivalent equation are derived from the magnetic flux path. Meanwhile, the proposed double rotor magnetic flux path, magnetic equivalent circuit, and the equivalent equation are also derived. Given from these two magnetic equivalent equation of air gap flux linkage, the stator and rotor poles reluctance are removed as these values are relatively small compared to the air gap reluctance. Hence, the final equation for air gap reluctance for both machines are shown. The expression of air gap magnetic flux linkage for the proposed machine is higher than the conventional machine. Apart from the torque improvement, the double rotor structure also allows the removing of platinary gear system while retaining the CVT function. The inner and outer rotor can operate individually and connected to each wheel for power splitting. In conclusion, the proposed double rotor IPM machine has torque improvement developed on the basis of utilizing the stator yoke flux of conventional machine, while it also fits the CVT function of hybrid electric vehicle application.
Swiss rotor machine is already known for more than 2 decades and it was a prolific machine. The advancement in fast switching power electronic Swiss rotor machine has been commonly used for industrial application. The basic principle of Swiss reluctance principle explains that the stator in phase A is excited with the current and then it forms a magnetic force, where the rotor attempts to swing at a counterclockwise direction for a minimum magnetic circuit reluctance, along with the diminished energy of magnetic circuit inside the machine. Whereas the phase A remains excited, the salient rotor pole remains still, as the energy minimum in phase A is achieved. Towards the constant movement of salient rotor, the next phase, which is phase B, is excited. As the rotor is started to shift away from phase A to phase B, the torque generation started to form. This event occurs because there is some flux which still remains even after the excited in phase A has been lifted. The remaining flux is accumulated around the stator pole pitch and ready to set off. At the same time, in the salient rotor leaves the phase A, the accumulated flux is detonated. The time when the accumulated flux goes off is the time when the torque is generated. For that reason, the design and the choice selection of pole arc in machine design to maximize the flux leakage is essential. To improve the performance of Swiss rotor machine, it was the first started by evaluating the magnetic flux flow around the Swiss rotor machine using finite element analysis. As the air gap flux leakage is the main factor contributing to the top performance of the machine, the stator and rotor pole arc of the machine has been improved to maximize the air gap flux leakage. Besides, it can be observed that the magnetic flux leakage around the stator yoke of Swiss rotor machine is not utilized. For further torque improvement of Swiss rotor machine by utilizing the stator yoke magnetic flux, an outer rotor is introduced to the conventional single rotor Swiss rotor machine. Hence, the air gap length can be further reduced to minimize the air gap reluctance. The introduction of outer rotor does not only maximize the use of magnetic flux as the air gap flux leakage, but it also nullifies the torque pulsation occurrence of the machine. The improvement of torque performance through an intro in the outer rotor can be proven through magnetic circuit analysis. As shown in the figure is the magnetic flux flow of Swiss rotor machine. The equivalent magnetic circuit and equivalent equation are derived from the magnetic flux path. Likewise, the magnetic circuit and equivalent equation magnetic flow in the double rotor Swiss reluctance machine is shown from the magnetic flux path. In conclusion, the magnetic circuit of the double rotor Swiss reluctance machine with increasing torque producing point through maximizing the use of magnetic flux.
Through this research work, the design of the proposed structure is patented under the Malaysian Intellectual Property this year. Also, the research outcome is disseminated in an international summit in India early next year. Part of the research also participated in the competition under the IEEE FIP competition and also CAD-CAM Product Lifecycle Challenge 2014. That's all for my research project, and thank you for watching my video.